Hello. So after successfully completing our understanding about the DC analysis and the AC analysis of this common collector configuration, please refer to the earlier video modules. We are now all set to run a time domain response of this circuit. So time domain, it means I have to use a time varying signal as an input and I have to see amplified output. So before that, let me be clear, the voltage gain of this circuit is approximately equal to 1. Theoretically, it is output voltage is always input voltage minus one drop less. That is drop across the base emitter junction of this transistor. And the current gain of this transistor circuit, which is the ratio of I out over I in, is approximately equal to beta, and beta is very greater than 1. For this particular transistor, the beta is 200 from his SPICE model, or you can also refer to the manufacturer data sheet. So now we are going to see the two signals in the output form. So I have used this voltage source as a sinusoidal voltage source. So I will right click here and I will show you that I have used this sine wave sinusoidal source where I have put up the parameters. So DC offset is 3.2 volt, that is providing a DC bias at the base because I haven't used external resistors for this circuit to provide a explicit biasing. So rather I would put the voltage source, DC voltage source, and I will superimpose a periodic waveform with a amplitude 100 millivolt, frequency 1 kilohertz, for example, and number of cycles 10. And here AC amplitude 1. Since I'm not running the body plot, I will just leave it blank. So, okay. So once that is done, now my DC bias points are like this. The voltage at the base is 3.2 volt. The voltage at the collector is 5 volt DC. So this diode is reverse bias. This diode is forward bias. The voltage here is 3.2 volt minus 0.7. So approximately 2.5. So I will have the output swing from 2.5 volt up and down. And I will have input voltage swings with the DC bias starting from 3.2. So I will have 100 millivolt riding up 3.2 volts and down 100 millivolt of 3.2 volts. So let us do that. I will click run. See here, before that, I forgot to show you that I have put up the spice command dot transient 0, start from 0, run it to 10 millisecond. At the steps of 1 millisecond, start saving data at 0 seconds. Now I am on the schematic. I will just click the input signal and I have this sinusoidal waveform that is starting from 3 point, as I said, 3.2 volt, 100 millivolt up. So from 3.2 volt to 0.1 volt, so it's 3.3 volt approximately up and 2.1, 3.1 volt down. So that's it. And now output voltage I would see on the same graph. In the blue, I am starting with 2.5 and it goes to 2.61. So approximately is about 0.7 volt is the gain. As I said, output will be input minus the VBE. That is the junction voltage drop here. So what I'll do, I will right click, I will add a plot pane, and here I will try to plot the ratio of output by input. I will say add V output divided by VB, which is my input. And you see I have again about average gain is about 788 millivolts. So it's just a 1 voltage drop. Yeah, so that's it. In AC analysis, we've seen that we have a voltage gain approximately equal to unity. So you always have a gain less than 1, right? So that's your output voltage, just near to 800 millivolts. How about plotting the current gain? Now add plot pane. Here I would click add trace. What I want to see here? Input current and output current, right? Because that's the current ratio. I said the current gain is beta, which is about 200 times. So output current should be 200 times than the input current. So here my input current, let's say, is IB of Q1. That is the current. It is about 13 microampere. So 12.5 to, so yeah, so 13 microampere peak. And then we'll add fresh, and output current is emitter current, right? That's what. And it is like the, you see it's like 2.7. So it's 200 maybe. Let me just zoom to fit, or maybe add plot pane, and here I will do like this. So just say zoom to fit, and this is going to 2.62 milliampere. So it's like about 150.2. Yeah, it's about 2600. Yeah, so we'll see that now. Add plot pane, and here I will rather plot the ratio of the current. Okay, delete the plot pane. So I will now say add trace, and let's say this is output current divided by input current, that is the base current, which is the beta. Actually, I'm plotting beta. So it's you can see now I'm getting an average about 202. That's the beta. And I just theoretically predicted the beta is 200. It's not predicted, it's from the SPICE model. So it's perfectly working as a amplifier, and it is an non-inverting amplifier. You see the output is in phase with the input right here. So this way you can perform the time domain analysis of your common collector amplifier. Try doing that with PNP transistor.